Hello and welcome to this video on bleach. That seemingly common chemical for many. A product you can buy in most grocery stores and even some hardware or big box stores. Well, sort of. Bleach is both the common name for a particular group of chemical formulations and the chemical process it causes. In purely chemical terms, it is just the process and not necessarily a particular chemical or group of chemicals. This is not a necessarily well-accepted distinction and often leads to a great deal of consternation. Unfortunately for those people, the facts do not care how offended or upset they are. Consider this your trigger warning if such things offend you. In a manner of speaking, you can compare the common term bleach and the important chemical difference to the way people refer to alcohol. If you have been drinking alcohol, using it, or similar, people are probably going to assume you mean ethanol, ethanol being one kind of alcohol. It is unlikely they will jump to something like methanol, isopropyl, or other alcohols. The same thing with bleach. Most people will apply the common understanding or name, if not meaning, instead of the technical or accurate meaning. There are a wide range of bleaches, but for the most part you can divide them into three categories, which thankfully are relatively limited: chlorine-based, peroxide-based, and sulfur dioxide-based bleaches. The names pretty much tell you what is there. Chlorine-based are based on chlorine with either hypochlorine or chloramine. A peroxide has something like a double-bonded oxygen, which is what peroxide is. Or you have sulfur dioxide-based, and well, its active ingredient, as the name would suggest, is sulfur dioxide, so nothing should be confusing or surprising so far. For most people, peroxide and chlorine-based bleaches are going to be commonplace, with your sulfur dioxide significantly less so. Chlorine-based bleaches are the kind found in supermarkets and hardware stores. Peroxide bleaches are found among cosmetics and wound treatment supplies. Both may be found in the serial killer section of your local big box store, most likely somewhere between the plastic sheets and shovels. You may also find them alternatively next to the rope. For the purposes of this video, let's start with the most common form of bleach. This is nearly always a formula including sodium hypochlorite in a water solution. The name basically tells us everything we need to know here. It's sodium and a chlorine with an oxygen attached. Chlorine-based bleaches are found in just about all household, if not most, household-based bleaches. You might also find them in what you could consider specialized products. But for the purposes of this video, we won't go into much detail on the role they play in sanitization or sterilization. They pretty much all do exactly the same thing though, and that is, they bleach clothing, laundry, surfaces, whatever it is that is exposed to them. You'll find that you very rarely, if ever, get a 100% chlorine-based bleach solution. Frequently, it's significantly less, somewhere down towards the 5 to maybe 20% range, and 20% is a rare high end. In short, 1 gram of 100% chlorine bleach would have the same power as 1 gram of chlorine by itself, and this is because it's effectively a ratio of 1 mole of each, although it's not quite right. It's simply having to do with how they work. Common examples of chlorine-based bleaches are sodium hypochlorite. Generally speaking, this is the example where it's going to be somewhere between 3 and 6%, and it is the colloquially referred to product known as bleach. There is also a calcium hypochlorite, which is effectively the same chlorine product, but rather than sodium, calcium is used. It's also sometimes chlorinated lime. You also have calcium hydroxide, which is calcium with a hydroxide molecule, the hydroxide molecule being an oxygen and a hydrogen. A calcium chloride, then you have chlorine gas, which is just chlorine by itself, and this isn't readily available for most individuals, and is generally used to bleach, let's say, a variety of products, more likely to be things like flour and similar. You might also find it used to disinfect water. There's also chlorine dioxide, which is, well, chlorine with 2 oxygens, and unstable gas versions, but these aren't used as much in household applications, or at least not deliberately. There are exceptions where this can happen, oftentimes leading to hospitalization. These are instead used in industrial purposes, things like, say, textiles where you want white fabric, for wood pulp creating paper, and so on. As mentioned, you might also find bleaches called monochloramines, halozones, and sodium dichloroisocyanurates. These are primarily used as disinfectants, not as bleaches, so we won't go into much detail on them beyond pointing out that these are somewhat distinct as a category. The next group are your peroxide-based bleaches. Peroxide-based bleaches are pretty much typified by a single bonded oxygen surrounded by something else, and this is useful as that single bond between the oxygens is very easily broken and means you get two free oxygen, or at least free positions on the oxygens that can bond to all kinds of other things or react with them, thereby bleaching whenever it's exposed to it. This is why the common chemical structure is R, oxygen, oxygen, R being anything else that could bond to that oxygen. For example, you could have a massive structure, or you might just have a hydrogen. It doesn't really matter which one it is. You might also sometimes see these called a peroxo group or peroxyl group rather than a peroxide. The common, or at least most common form of peroxide is hydrogen peroxide, and that is exactly the example given, a hydrogen on each side of the oxygen. When the peroxide is broken, you basically get an oxygen and a hydrogen, which is part of the way to water, and that allows it to react to all sorts of other things. It can be useful, but then again, it can also be rather dangerous because it is very reactive. It is sold in a wide variety of concentrations and solutions, but for the most part you'll find that the most common formats are going to be organic peroxides. That is, they have carbons on each side initially, and then you have the oxygens in the middle, or something similar. The most common example, hydrogen peroxide, is used for things like bleaching wood, but also for hair and other similar things. To use a very common and simple example, it is what you would find in blonde hair dye. Then you have sodium percarbonate. This is a relatively larger molecule, certainly by comparison to hydrogen peroxide, but what it makes up for by being somewhat larger is that it's a little more useful in water, because it can dissolve and it yields two different products. These two different products are helpful as they not only bleach, but they also, to a certain extent, can add some emulsifying and cleaning properties to it. So this is something you would find in both laundry and dish detergents in some cases. Then you have sodium perborate. This is sodium with borate at the end. When used, it effectively forms hydrogen peroxide, with a small anion spun off. Then you have peracetic acid, which is effectively acetic acid with the necessary peroxide group, and it's often used for disinfection and water treatment rather than for its bleaching, although some products may contain it. Another common example, although perhaps one that's more controversial than the others, is ozone. Ozone technically doesn't come under the heading of peroxide, but you'll find that when it's in an environment, say for example an aqueous solution, water effectively, it turns into a peroxide along with other things, and performs practically the same role. Potassium persulfate is much like the similar products such as sodium. You then have permanganates, and the example we're thinking of particularly here is potassium permanganate, which is potassium, manganese, and 4 oxygens. This is effectively a double whammy, in that it has two groups of oxygens that make it much more effective at its job. These are less frequently used in direct application to the human body, but instead more in preparation of food and similar. As you can see, these bleaches are not used as frequently for personal use, or at least not personal use that should be invasive. In fact, no bleach should be used invasively. However, some people are hell-bent on testing Darwinian evolution and humanity's attempts to get in the way of natural selection. The next category we have are reducing bleaches, and these are effectively going to interact with the compounds directly in a manner of speaking, and by doing so, they're going to pull off an electron from the targeted chemical, let's say, and when that happens, you alter its structure and you alter the structure of these bleaches. Sodium dithionites are the first example we have for you, and in order for these to work, it has to undergo a series of reactions. In order for that to happen, as mentioned, you not only need the original chemical, let's say, as your initial reagent, plus whatever it's targeting as another reagent, and then you need to hope that the products generated aren't going to cause a worse effect. This is why it's almost never used in domestic settings, and in fact, its primary role is in industrial dyeing or similar. When this happens, you effectively turn, say, wood pulp, cotton, or wool, or even clay into a much more pale product. The final group we have for you is actually photographic bleach, and this is actually useful in terms of something that occurs in, well, everyday life. The first and most obvious examples for many people, if they're old enough, would be photographs, and the whole idea of resolving a photograph using light. The metallic silver that is used in the development of photographs reacts to light, and that reaction causes it to bleach in parts. That bleaching causes the EDTA that's used in solution to fix in position. This allows you to create an image and sort of permanency, although several steps are then used afterwards to make sure that the image stays as it is. An alternative approach is to simply expose silver, and specifically here we're talking about a kind of silver that's not necessarily elemental silver, or rather it's potassium dichromate, and when you have this and you expose it to light, it's either going to make it lighter or darker in the places where you need it to be. Now for how bleaches work, and as mentioned, some of these are much more obvious and some of them are much more convoluted. For most organic materials, you're going to find that the colour is generated by pigments. Now these pigments can be something as simple as, say, phenols, although phenols are by no means simple. Is simply an example that's commonplace by comparison to others. When you start breaking the chemical bonds, for example by introducing those oxygens from a peroxide solution, the molecule no longer has the same structure, and because it no longer has the same structure, it no longer absorbs light, or more accurately reflects light in the same way. This is helpful, as if it's either going to increasingly absorb light, you're not going to see anything because none of the light is bouncing back to our eyes. Conversely, if it changes how the light is reflected or not absorbed, you instead see a shift in the coloration. Chlorine is particularly useful for this, but it's also the same way that peroxides work. Reducing is effectively the same idea, except it involves breaking a double bond. By breaking a double bond and reducing it to a single bond, you're able to effectively grab parts of other molecules and, again, change their structure. But this then affects the absorption of visible light and generally will increase the absorption. As a general rule, light, and this could be sunlight or other means such as that used in photography, has a slightly different avenue of action. Rather than relying necessarily on the, let's say, interaction of chemicals that bleach, it instead relies on the energy imparted to those molecules, and that energy, let's say, disrupts the bonds of the molecules. When this happens, you again get changes in structure. That change in structure leads to a difference in the amount of light absorbed or reflected. It either diminishes the amount reflected, or it increases the amount absorbed. This then leads to what we perceive to the human eye as discoloration. Occasionally you may also see it as a very light blue, but this again owes to the nature of light, and it's true of all bleaching mechanisms for that matter. This is what bleach is. Your household bleach might bleach things, and that is a process, but it is just one of many possible bleaches, or more accurately, bleaching agents that exist in the world, and ultimately they all rely on a very similar phenomena. how they get to the end result will vary drastically, some relying on more direct methods, others relying on intermediaries, and others again relying on external sources of energy. But they all achieve the same end result. They prevent light that hits let's say, a pigment or stain, whatever it happens to be, and either increases the absorption of that light or prevents it from being reflected as readily, thereby reducing the human perception of it, giving us the idea that it's bleached or that there is less of that thing there, causing the coloration. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you might have below.